about attraction schemes, and the first speaker is Sarvesh Dubey about slope-limited transport on icosahedral grids. Thank you.
Good morning, everyone. I will be talking about slope-limited transport schemes using icosahedral hexagonal grids. This work was supported by IPSIPAR, Interference Center for Advanced Research, and it was supervised by Thomas Dubose and Frederic Houdin. So the motivation to use this hexagonal grids for the advection scheme is because of the well-known pole problem, which is because of the convergence of the meridians at the poles, which is source of various problems in latitude-longitude grid. And on the other hand, icosahedral grids are quasi-uniform grid, and there is no pole problem. So these grids are quite good for parallel techniques, and there is also a choice which type of grid you want to use, because we can either use Vernoid type of grid, or we can use the Vernoid triangulation. And this is why we are using these icosahedral grids to develop advection schemes. But schemes are not grid specific, and any grid can be used with these advection schemes. So this is the outline of my talk. I will first discuss about the two gradient reconstruction, on which my advection schemes rely, and then I will discuss separately the two advection schemes called the semi-Lagrangian type finite volume scheme and the method of line-based finite volume scheme. And then I will describe the slope limiter I am using. After that, I will briefly describe the advection test cases I am using for this work, and then the results of those advection test cases for the both schemes. And in last, I will compare few test cases for the flux corrected transport and the slope limitations. So from the triangular grid, we can construct a hexagonal grids. We are constructing by two ways. Either we can use the circumcenters of the triangular grids to construct a hexagonal grid, or we can use centroids to make a hexagonal grid. In both cases, we will address these vertices of the triangular grid as generators, because these are the points which we are using to generate our primal hexagonal grids. So now the finite, this is the first gradient, which I call like finite difference gradient. In this gradient, to compute a gradient for the hexagonal cell, we compute 6 or 5 gradients, which is depending upon the fact that the control volume is pentagon or hexagon. If it is hexagon, there will be 6 constituting triangles, otherwise there will be 5 triangles, and we compute these 6 or 5 component gradients. To compute these gradients for these 6 or 5 triangles, we assume that the gradient of this triangle is such that the change of along this gradient along this great circle arc is phi gk, like the value of phi, the scalar field here and here. The difference is equal to here from here, and this is like the difference the change in the along the gradient along this edge is equal to the value of the scalar field here minus value of the scalar field here. And in last, we assume that the gradient is tangential to this cell center of the hexagon. And after this computing these 6 constituting gradients, to compute the unique gradient, we just take a simple average of these 6 gradients. The problem when we use this finite difference gradient in sense of finite volume scheme is that for finite volume scheme we have inputs as average values, and in this scheme we are using point wise values to calculate this finite difference gradient. The second gradient is well known, like gradient using Green theorem. In this this cell average gradient is converted to surface or line integral, and then we approximate this with the values and the geometry of the grid. Here we introduce this extra term to ensure the fact that if our field is uniform over a sphere, the gradient of that uniform field vanishes. So this is an extra term which ensures that gradient vanishes if we are using a uniform field. Also, we have the same problem here, because if we are using a finite in a finite volume sense, the values the values phi k are only a first order approximation, not a second order approximation. And this is the scalar field I am using to compute the performance of this gradient, and this is the result for L2 and L infinity norms over VT grid structure. VT grid structure is one in which we use the circumcenters to construct the hexagons, and this is the result for the BT grid. BT grid is the grid in which we use the bicentric or centroids to construct the hexagon grid. In both cases, we see that the L infinity norm is inconsistent and it's not converging. So because we are using in finite volume sense. So to avoid this inconsistency, we have two options. Either we can use the centroids of the control volume, this which is our hexagon, instead of this generators to do all our calculations. Otherwise, we can simply use some grid optimization which will reduce the error. We have this both option in our work, and we also use this this optimization known as layout optimization. In this optimization, we start with our generators and simply compute our corners, which could be either circumcenters or centroids. After that, we compute the centroid of our control volume, which is this simple by simple averaging, and then we replace the old set of generator with this centroids, and we again start from the first step, and we do this like 2000 iteration, because like it has to be done only once, so it's not very computationally very costly. And after grid optimization or with modification, we have these results. This C is like this C is stands for like the grid with modification, and this is for the optimization optimized grid. So in both cases, like this is with modification in grid, in which we use centroid instead of generators, and this is the grid when we optimize the grid. In both cases, we see that now L infinity norms is also converging, except like I have some problem with VT grid system, because in VT grid system L infinity norm it starts becoming bad with finite with very fine resolution. I'm not sure, maybe this is because of some accumulation of some error, and but for the BT grid I don't have any problems, and everything is converging with second order accuracy. These two reconstruction can be used to construct a linear reconstruction like this, and in both our advection schemes we will use this linear reconstruction. So this is the flux form of tracer continuity equation, and we can discretize this continuity equation for a control cell K. This is the area of that cell, and this is the average value of the rho phi over that cell, and we have used Green theorem, and this nk stands for like the number of edges of that control volume. In our case, it could be either 5 or 6, and this equation can be written in a compact form, like the evolution of this quantity is because of this fluxes, and evolution of this mass is because of this flux of masses. Here, like mki and fki are the instantaneous values of the mass and tracer flux on the edges. Now this is the first advection scheme, which is like known as I call it like semi-Lagrangian type finite volume scheme. In this scheme, we integrate this equation first in time from from one time step, and we get this thing like here this big fki is basically the time integrated value of small fk, and big M is like time integrated value of this small mk, and basically this big mk is the amount of air going out from this particular edge, and this fki is the amount of tracer going out from this edge, and we approximate this value of this flux by the mass and the average mixing ratio of this departed region, following like we are using a Mura type of scheme, and we approximate this departed region with a parallelogram, and we always assume that this parallelogram will be on the upwind side in only one cell, and we ignore any branching to make it simple, and we approximate this value of the like mean mixing ratio in a like by computing this backward trajectory where Vki is the speed of the fluid, and Rki is the midpoint of that edge, and Ck is the centroid of the control volume. In the second scheme, which is like called as method of lines based scheme, we approximate the small fluxes, instantaneous fluxes, with the value of the instantaneous value of the mass and the value of the tracer mixing ratio on the midpoint Rki of that edge. And when we substitute this value in our equation, we finite this discrete equation, we get this this equation, which is like semi-discrete, and we can then use then we are using Runge-Kutta third order scheme to integrate it forward in time. In general, both these schemes are not positive definite, they are producing lot of negative values also and overshoot sometimes. So we are using this slope limiter. This is a very crude Van Leer type of slope limiter, and in this slope limiter what we do, we just replace our computed gradient with this new modified gradient where alpha k is a factor which is determined by this coefficient. Basically this we check how the tracer is changing inside the cell and how the tracer is changing around the neighborhoods. If both these values are in agreement with each other, we take the minimum. Otherwise if these values are opposite in sign, we make them 0. And when after computing this modified gradient, we use this gradient instead of our initial gradient reconstruction in our linear reconstruction. In this alpha k, like this coefficients, we need to compute the maximum value of the tracer mixing ratio inside the cell and minimum value of the tracer mixing ratio inside the cell. For that we use the unlimited gradient, and this distance like the distance of the corner of the hexagon from the centroid. And to check these two schemes, I am using the test case suit proposed by Lloydson and al. And these cases are like after half of the time interval, these winds change their directions, and So after full time, everything is back to its original position, and we know the final solution, what is the solution, analytic solution. And this advection test cases I used in here to calculate the order of numerical convergence of these two schemes, ability of how they are preserving the filament, and how they are transporting rough distributions, and how well they are keeping the pre-existing functional relation between two tracers. This is the first test case. We are using Gaussian hills to compute the maximal order of convergence, and there are like un is with superscript un means it's not without any limiter, and with sp means it's with slope safe preserving with limiter. So we can see like when we are using our limiter, we have a small increase in the error coefficient, and especially the L2 norm is close to the without like the real scheme without slope limiter, but there is a shift, and this error constant increase for L infinity norms. But for the method of lines, all well, with or without limiting, the schemes are quite close to each other, and although this convergence is fast, but I think like after some fine resolution, the convergence of method of lines also becomes faster. Now, initially it's not that good, it's approximately first order, but with increasing resolution, this convergence is improving. And this is the empirical convergence rate derived like using least square feet. And for this SLFB, it's the unlimited scheme is around 1.5, and for this method of lines it's like 1.4. So it seems like SLFB is working better in terms of maximal convergence, and we can see that for both the schemes using this limiters are not affecting very much, although I think like it's affecting most of the time the L infinity norm. As we see, it's affecting the L infinity norm, not as much as L2 norm. L2 norms are basically not changing very much. This is the filament diagnostic test case. In this test case, we define the area, this area which is like this is tau is the threshold value of some tracer mixing ratio, and we sum all those area having this tracer values greater than or equal to this threshold value, and then we define this filament preserving diagnostic, which is like this. If we are in a non-divergent flow, this ratio should not change, and it should be constant, but it's not the case for Eulerian schemes most of the time, and I think this is the results for finite SLFB and FBML. And this is this third test case is checking the how well these two schemes is preserving the pre-existing functional relations, and both of these schemes are able to preserve the linear correlation exactly. And when we are using this correlated cosine Bell and cosine Bell tracers, which is like this is the functional relation. This is the scheme without slope SLFB scheme without slope limitation. So we see some outshoots, and this is the scheme with slope limiter. We see the these outshoots are gone, but the scheme is slightly diffusive because of the slope limitation. This is the same result for method of lines based finite volume scheme. Also here we see the slope limiter is able to remove this outshoots. And one plus point what I think like if we see this SLFB scheme, we see that without slope limitation and with slope limitation we have a small amount of this unmixing, while in this method of lines case we don't have we have very small, very like 100 times smaller unmixing even without slope limitation. So this is a benefit, I think. It's only doing either real mixing or overshoots, and this overshoots can be removed using this slope limitation or slope limiter. This is the result for the transport of rough distribution like slotted cylinder, and this is the result for the very fine resolution like 192 is 1922 is around 0.375 degree for in my case, and this is the at the half of the time interval, and this is at the full. This is MLFB and this is SLFB. We can see both his schemes are doing almost exactly same. Maybe SLFB is slightly more giving slightly more good maxima, but this is not really visible because so like for fine resolution the results are almost same for both of this scheme, I think. And in last I will I will talk about this comparison of this flux rated transport and the slope limitation. I am using Zalizek FCT approach, and this SL stands for the slope limited and this FC stands for flux rated transport. So we can see the difference like for this convergence of Gaussian hill is the L infinity norm, and this only this L infinity norm is having this larger error constants, and otherwise the L this convergence like empirical convergence rate is almost equal for slope limitation and for the flux rated transport. This is the result for the filament projection diagnostics. This is the case, this is the result for the pre-existing functional relation, and here we see that for the flux corrected transport we have a higher amount of unmixing, while this if we are using slope limiter, this unmixing is smaller as compared to the old one. We also use this slope limited finite volume scheme with 1D Van Lee type advection scheme in vertical to develop a three-dimensional advection scheme, and we tested some DCMIP test cases of 2012, and we have this results like this is the result of the deformation test case, and Q1 is the Q1 and Q2 is the cosine bill and correlated cosine bill, and this is the function relation, and we have this result like we have this real mixing and say preserving U mixing, but we don't have any outshoots, and this is the Hadley type of circulation in which at the like half a total hour we have this this stretching in the field, but after 24 hours it comes back to its original state, although it's not very nice looking. So it's the summary. In absence of any special treatment, gradient reconstruction is inconsistent if we are using it in a finite volume sense, and either slight modification in grid or any grid optimization can solve this problem. Two simple advection schemes are proposed using this linear reconstruction, and both of these schemes are not really say preserving or fastly definite. So we are using a slope limiter, but this slope limiter is successfully avoiding any spurious oscillations. We compare slope limiter with FCT, and we found that slope limiter is slightly more diffusive, but at the same time slope limiter is not producing like higher values of non-physical mixing as FCT is doing. And in last we use this SLFB with slope limitation and Van Lee scheme in vertical to develop a 3D advection scheme. So finally we conclude that slope limitation can be used to construct a second order partially definite advection schemes. Thank you.
Yeah, thank you. One small question. I was just wondering how about other properties like positivity or conservation?
I'm using like in finite volume space, so conservation is achieved automatically, and when I am using the slope limitation, it will give me positive values, like positive definite.
Okay, that works.
Thank you.
Thank you again.